Okay, we are at the last section, section 9.9, rocket propulsion. The Up to this point, we've been discussing the change in momentum, delta P. We've always assumed that the mass was constant and it's only the velocity that's changing. So we've written it as delta m delta v. Well, that's no longer the case. You know, as a rocket is expelling fuel, its mass is changing. So it's really a delta m delta v. Momentum is or delta momentum. Delta p is equal to delta m times delta v, and we're going to delve into that in this section. So, you know, when you're in your car, the engine is turning the wheels, and the wheels are spinning on the, or not, hopefully not spinning. They're turning on the pavement, and it's the friction that drives you forward. Or if you step on the brakes, the tires, the friction of the tires brings you to a stop. But as we go up in space, there is no road that the rocket is acting upon. So it's really just the ejection of the fuel that causes the um, rocket to go. I think when we were talking about the laws of motion, I blew up a balloon and I let the balloon go. It was the air molecules ejecting out of the collapsing balloon that forced the balloon forward, and that's kind of the idea. You have the expanding gases that, ejecting out of the back of the rocket that causes the rocket to go forward. Um, there was actually a time that they didn't believe rocket uh, propulsion was possible because they thought, well, the gases have to push against something. But you know, as we learned, it's just the mass of molecules coming out of the exhaust that actually pushes the rocket in the opposite direction. Um, so the system that we're going to be looking at is the rocket plus its ejected fuel. And as the fuel is ejected, the mass of the rocket is changing. Um, so uh, so since it's a rocket plus its ejected fuel, it's a isolated system. There's no external force pushing on the rocket. It's all coming in. It's all coming from the rocket itself. This is similar to, uh, you can imagine this archer on ice. Every time he shoots a bow, he gets a little bit more acceleration from the mass of the bow going, and you know, he's pushed in the opposite direction. It's kind of the cannonball and cannon that I spoke of earlier. But um, again, as the rocket propels forward, it's losing mass. Here the untethered astronaut he's moving about by the uh, short bursts of nitrogen gas. He's using short bursts of nitrogen gas um, to propel himself. Um, so we're going to look at the rocket equation. Now we have, um, since it's an isolated system, the change in momentum, delta P, is equal to 0. So that P initial is equal to P final. The initial momentum is equal to the final momentum. So here we have mass times velocity. The momentum is mass times velocity. Well, it's the mass, the big mass is the rocket and fuel system, minus the delta mass is the bit of fuel that you're ejecting. It's already going at a velocity, and there's a change in velocity, delta v, and that's equal to, I mean, we add to that the change in mass, the delta m that's being ejected, times the velocity, the initial velocity is going to, minus the ejected velocity. I mean, the velocity of the ejected material, the gases coming out. So let's see. So if you expand that, you know, if you multiply the m minus delta m and the v plus delta v, if you multiply those out, you get a long equation. Mv equals mv plus m delta v minus delta m, v minus delta m delta v plus delta mv minus delta mve. You can multiply all that out. That's what you get. Well, there's parts that cancel, and when you end up, you can do it yourself and see. You end up with big M delta V minus delta M delta V equals V ejected, the velocity of the ejected material, times the change in mass, delta M. And we'll see that the change in velocity is equal to V delta M divided by M minus delta M. Now, if we look at the time rate of variation, delta t gets very small, so we look at it as dv and dm. Well, the dm and dv are such small quantities. You see that in that second equation, you have on the other side of the minus, you have a delta m delta v. Well, as we make those smaller and smaller, they become negligible. So we end up with mdv instead of m delta v. We say mdv is equal to ve dm. Well, the dm, the change in material being ejected, is minus the loss that the big M is having. So we can substitute, instead of dm, we can say minus d big M. So our equation becomes mdv equals minus v ejected dm. So if we integrate from v initial to v final of dv, that's equal to, we're integrating both sides. First we divide both sides by m, then we integrate. So the integral of from v initial to v final is dv equals minus ve, the ejected velocity, integral of initial mass to final mass of dm over m. Well, if you work that out, you'll see that v final minus v initial is equal to ve times the natural logarithm of m initial divided by m final. Let's see if there's something I need to. So what does this tell us? It tells us that the increase in rocket speed is proportional to the exhaust speed of the ejected gases. So the exhaust speed should be very high. And the increase in rocket speed is proportional to the natural logarithm of the ratio of initial mass to final mass. So the ratio should be as large as possible. The mass of the rocket without its fuel should be as small as possible, and the rocket should carry as much fuel as possible. So those are two takeaways that we get from that bottom equation. And now thrust is the force on the rocket, which it's mass times acceleration. Well, what is acceleration? Mass times acceleration is mass times dv dt. And that's also equal to the absolute value of VE dm dt. Let's see if we see that from, you can see that from that middle equation. The time rate of change of velocity is the acceleration. So mdv is equal to minus VE dm. Put the absolute values, it just becomes VE dm dt. We're doing the time rate of change, and this shows us that the thrust increases as the exhaust speed increases, and as the rate of change of mass, called the burn rate, increases. So the burn rate and the exhaust speed are very important in thrust. So and I think that's it. That's the end of the equation. So I wouldn't say that you're rocket scientists now, but you understand a little bit more about rocket propulsion. All right.